Hello, in this video, I'm going to show you how to find a correlation coefficient using Excel, and then we'll talk about linear regression and finding how to estimate the linear regression equation. So we have two variables here, speed and distance. Speed is the speed of a speed that you are using your golf club to hit a ball, and distance is how far the ball travels after hitting it. So we have the explanatory variable speed because it happens first, and this causes the ball to travel. So distance is the response variable. Now let's first check with the scatter plot how they are related. I'm going to click on insert and then click on this scatter plot. Okay, so we have distance on the y-axis and speed on the x-axis. They are plotted like this, and it looks like that they have some positive association as the higher the speed, the higher the ball travels. That means the higher the distance. And if I add a trend line, it looks like this. Now, this line is going to come handy later when we'll talk about regression. But first, let's think of the association between speed and distance. I'm going to hide this graph for now. Okay. To find the linear association or the correlation coefficients, we have to use formula. First, we need to get the means. That is easy to find in Excel. So average of both of the variables. So average is 101.875, and the average of the y variable is 266. I'm just gonna put it in different colors so that you'll understand that this is not included in the data set. And now we have this opportunity to calculate the distance, the gap from xi minus the average. So sample average over the standard deviation of x, that is Sx. All right. So to find the value of Sx, or the standard deviation of x, let's calculate the Sx as well. So I'm going to write standard deviation, that is sample standard deviation because we have a sample here. The standard deviation is 2.29, and then standard deviation of y is 7.74. All right. So it's easy for us to find this number. So we have x here. Xi means x1, 2, 3, 4, 5, 6. So when you go from this way to this, so this is x1, this is x2, this is x3. So this means for each x, we're going to subtract the mean, the sample average. So parenthesis, then this minus the sample average, this. And I'm going to put a $sign here so that this row doesn't change. I have fixed the number of rows, which is 10. Then I'm going to close the parenthesis and then divide by the standard deviation of x. And for this row as well, I'm going to fix this. So a $11. So I'm going to fix that $11 so that I can use this same formula to calculate these numbers for all these values. Okay, I'm going to press enter now, and I have this number. And then I'm going to drag this little tiny rectangle over there down below so that I get all the values. Okay, cool. I'm going to do the same thing for y. And then that means yi minus the sample mean of y over the standard deviation of y. Okay, so that means I can just copy and paste it here and then change this formula. So this looks correct. I'm going to use b2 minus the mean of y over the standard deviation of y. So this looks correct. Pressing enter, then drag this little rectangle down below. So I have both of this number. In a way, what I did here is I kind of calculated the z-score. So I subtracted the means and then divided by standard deviation. Why? Because speed and distance, they are in different units. So using this, I'm calculating how many standard deviations away these values are from their respective means. How many standard deviations away these values are from their respective means. Okay, now what I'm going to do is multiply these two values. Why? Because this is the requirement for the formula for correlation coefficients. And I'm multiplying these two values, and then for all of these numbers, I got these multiplied values. Okay, now I'm gonna sum these numbers. All right, and that number is 6.5708. So my correlation coefficient here, correlation coefficient equals to R equals this number, which is this number over the count of observations, the number of observations I have. Let's say this. So how many observations I have? 1, 2, 3, 4, 5, 6, 7, 8. 8 observations, but I'm gonna have to subtract 1 to ensure that I have considered the mean that I've used. Since I've been using the mean, so I lose 1 degree of freedom. So subtract 1 and then press enter. So the correlation coefficient is 0.938696. That means if I round it to 3 decimal point, 0.939. That's a strong positive correlation as we see here. What does that mean? That means these two variables are associated or correlated in a way that's linearly represented by their correlation coefficient as 0.939. And notice that in a way, we are checking the average of the multiplied form of these scores, these standardized values of these numbers. And it has an interesting property. You know how you find the area of a rectangle. You multiply height by the width. And if the height increases, then the number for height goes bigger, and if you join two corners of this rectangle, that line goes up, that line goes steeper. In the same logic, you see that if their correlation goes up, then this line will be steeper. Okay, now that we have the correlation coefficient and it shows the linear association between two variables, that means their variations, each of them has their respective variations, and their variations are related somehow in 93.9% of the cases. Now, another way to check the association between two variables is put them in some type of equation, like regression equation. Let's say if we want to predict the value of y equals, let's say, b0 plus b1 times x, like this. The reason we need this is like for some value of x, we want to predict the value of y. And that's why we need to understand the values of b0 and b1. These are estimates for the true values of beta 0 and beta 1. You can look it up on your lecture notes. But the bottom line is that we are trying to find the slope of this line, which is b1, and we're also trying to find the intercept of this line, which is b0. Okay, now let's calculate b1 first. To calculate b1, we have a formula, and that formula is, we can express the formula in terms of the correlation coefficient, and that formula is b1 equals r times sy over sx, and that is the correlation coefficients times the standard deviation of y over the standard deviation of x. This is easy for us to calculate because we have already calculated the correlation coefficient. So correlation coefficient times the standard deviation of y, which is here, over the standard deviation of x, which is here. So b1 equals 3.166102. I'm going to round it up to 3 decimal points. And then how do we find b0? b0 is y bar let's type here b0 is y bar minus b1x, and that is, it's easy to see, sorry, I need to use x bar. It's easy to see where this expression came from. So you have y equals b0 plus b1 times x. We just changed the side. And we have this because using this equation, what we're trying to do, we are trying to predict the values of y on average, because we cannot predict we cannot predict exactly these values. What the values of y we predict is on this line. So for each values of x, since we are using this linear equation, we're going to get the values of y exactly on this line, not on these dots, because we are using a linear function, linear equation. Okay, so that's why if we use x bar or the mean x, then we can get the mean y here to get the value of beta 0. And that will be true for any points on this line. You plug in any values of x, you are going to get the respective value of y. Okay. And since we have both numbers here, I'm going to type in. So the y bar, we can get it from here minus the value of beta 1, this, times x bar, which is here. Okay, so beta 0 is equal to negative 55.796. So this equation, now we have the values. So this equation y equals negative 55.80 plus 3.166 times x. So now if we want to calculate the value of y, if we want to predict the value of y for which we don't know, we don't have the observations here, we can still do it. Let's say we have, for x, we have 100, 102, 103, but we don't have any 104. So we can predict the value of y even if we have x equals to 104. And that y is going to be somewhere here on this line. We can try to do this. So negative 55.80 plus 3.166 times 104. So this predicted y or y hat is 273.46, and that is the value of this point here, 273.46. What if we use 103? If we use 103 here, we're getting the value of this point on this line. So 270.29. Notice that there is a gap. There is a gap in our prediction, and that's because there's a gap between the actual number and the number we received from this equation, which is going to give us the point on this line. So the true value of y for x equals to 103 is, from here we can check, 274. So the actual value, actual y or observed y, is 274. 274. But the predicted y or y hat is what we get from here, and these are both at x equals to 103. So the gap between the actual or observed y and the predicted y is this, and this is our residual or the gap in the prediction. Notice that we set the line in a way that sometimes the residual will be positive and sometimes will be negative, but on an average, the residuals will be zero. That means the line exactly goes through the middle of all this data variation. Okay, hope it was helpful. Thank you very much, and I'll see you in the class.